An organ pipe is used to make a fundamental tone of 64 hertz. That's a low note. Okay, the speed of sound is 320 meters per second inside the pipe, so it's maybe a little slower because it's confined, or maybe it's cold or something, right? If the pipe is one end open, one end closed, what length should it be, right? So here's this pipe, right? And then the fundamental looks like this. Looks like that. That is 1/4 wavelength. Okay, so we want to know what length it should be. L equals, right? And it's 64 hertz, so we can figure this out. First, I think we ought to figure out the wavelength, shall we? All right, so V is F lambda, so therefore lambda is V divided by F, right? So the velocity is 320 meters per second. The frequency is 64 hertz. Okay, so the wavelength is 320 divided by 64, and that's 5. 5.0 meters is the wavelength, right? Okay, so how long should the pipe be? Well, we can do this, right? This is 1/4 of the wave, so we say L is 1/4 of the wavelength, right? And the wavelength is 5 meters. Ta-da! So L is 1/4 of the wavelength, and 1/4 of 5, so 5 divided by 4, is 1.25. Okay, so 1.25 meters long. And then what are the next two frequencies that it can make? Well, there's a simple way. I'm going to do the simple way here, and then I'll pause, and then you can see why it's that way. Okay, but the simple way is that these pipes, the way they go is they go the fundamental frequency, 3 times the fundamental frequency, 5 times the fundamental frequency, 7 times the fundamental frequency. They go 1, 3, 5, 7. They do odd numbers, okay? But I'll show you that in a moment here, okay? If that works for you, we're all set, right? So 3 times, the next would be 3 times 64. 3 times 64 is 192, right? Hertz. And then 5 times 64 would, of course, be 320 hertz. This is 5 times 3 times, right? Okay, now I'm going to show you, if you can stop there if that makes sense to you. I'm going to show you why this is in a moment here. Shall we? All right, so the fundamental looks like this, right? It's like, right, and then here's we'll draw these pipes here. Okay, these are all 1.25 meters long, and here's the fundamental. The next one looks like this. I'm just learning how to do, ooh, that was pretty good. That was really bad. Okay, so this is 1/4 wavelength, right? So 1.25 is 1/4 wavelength. So the wavelength is 5 meters. Okay, this one is 3/4. So we go boop, 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 right? So 1.25 is 3/4 wavelengths, right? And then this is, let's do it. Let's see. This is 1, 2, 3, 4, 5/4 wavelengths. So 1.25 is 5/4 wavelengths, right? So here the wavelength would be 4/3 of 1.25. So 1.25 times 4 divided by 3 is 1.6 bar, right? And then here the wavelength is going to be 4/5 of this guy. So 1.25 times 4 divided by 5 is 1. Okay, lambda is 1 meter. Okay, so now for all of these guys we can figure out the frequency, right? 320 divided by 5. So frequency is velocity over wavelength, right? So 320 meters per second divided by 5 is, of course, our 64 that we got it from, right? We got the 5 meters from that, right? And then this guy, the frequency is 320 divided by 1.6 bar. Okay, so 320 divided by 1 point, a lot of sixes. All right, that's 192. Okay, and then this guy is 320 divided by 1. I know what that is. That's meters per second, right? Divided by 1 meter per wave, right? That's 320 hertz. Yeah, that's why they are that way.